Welcome to G Fun Facts Online. Today we're diving into one of the biggest puzzles in all of science. It's a story about a single number that describes the entire universe. A number that we thought we understood, but which is now threatening to break cosmology. This is the story of the Hubble Constant and the cosmic crisis it has created. In astronomy, there are few things more fundamental than the expansion of the universe. We know it's happening. But the big question is, how fast? The answer is encoded in a value called the Hubble Constant. The problem is, our two best methods for measuring this constant give two different answers. This isn't a small rounding error. It's a deep, statistically significant disagreement that suggests either our measurements are wrong or our entire model of the universe is incomplete. To understand this tension, we have to go back to the 1920s. At the time, the prevailing wisdom was that our Milky Way galaxy was the entire universe. Everything we saw was thought to be inside it. But astronomer Edwin Hubble, working at the Mount Wilson Observatory with the most powerful telescope of his day, wasn't so sure. His work stood on the shoulders of giants. First, Vesto Slipher had noticed that light from many distant fuzzy objects, then called spiral nebulae, was redshifted. Just like the pitch of a siren drops as it moves away from you, the wavelength of light from an object moving away from us gets stretched, shifting it towards the red end of the spectrum. Slipher's work showed these nebulae were moving away from us at incredible speeds. The second key piece came from Henrietta Swan Leavitt, an astronomer at Harvard. She discovered a remarkable property of a special type of star called a Cepheid variable. These stars pulsate, getting brighter and dimmer over a regular period. Leavitt found that the longer a Cepheid's pulsation period, the greater its true, intrinsic brightness. This was revolutionary. It meant Cepheids could be used as standard candles. Imagine you have a 100-watt light bulb. If you see it from across a field, it looks dim. But because you know it's a 100-watt bulb, you can calculate exactly how far away it is based on its apparent dimness. Cepheids work the same way. By measuring their period, we know their wattage. By measuring their apparent brightness, we can calculate their distance. In 1923, Hubble found a Cepheid variable star in the Andromeda Nebula. His calculations placed Andromeda at a distance far outside the Milky Way. It wasn't a gas cloud in our galaxy. It was a separate, colossal, island universe, all on its own. In that moment, the known universe expanded astronomically. Hubble then combined his distance measurements to many galaxies with Slipher's redshift data. In 1929, he announced his groundbreaking discovery. The farther away a galaxy is, the faster it is receding from us. This elegant relationship is known as Hubble's law, and the rate of that expansion is the Hubble constant. Now let's fast forward to today. The current crisis comes from our two most precise methods of measuring this constant. They represent two different ways of looking at the universe. One looking at the universe nearby, or the late universe, and the other looking at the universe in its infancy, the early universe. Let's start with the late universe method. This is called the cosmic distance ladder. It's a step-by-step process for measuring ever greater distances. The first rung is parallax. This is the most direct method. Hold your thumb out and close one eye, then the other. Your thumb appears to shift against the background. By measuring this tiny shift for a nearby star, as the Earth orbits the Sun, we can use simple trigonometry to calculate its distance. This works for stars relatively close to us. The second rung uses our standard candles, the Cepheid variables. Astronomers find Cepheids in nearby galaxies whose distances have already been measured using parallax. This allows them to perfectly calibrate the relationship between the Cepheids' pulsation period and their true brightness. Now they can use Cepheids to measure distances to more remote galaxies, out to about 100 million light-years. For the third rung, we need an even brighter standard candle to see across the universe. We use Type Ia supernovae. These are cataclysmic explosions that happen when a white dwarf star in a binary system steals too much matter from its partner and blows itself apart. Because they all explode at a very specific mass, they all have nearly the same peak luminosity, making them fantastic standard candles. By finding these supernovae in galaxies where we've also measured Cepheids, we can calibrate their brightness and then use them to measure distances billions of light-years away. By measuring the distances and redshifts of these faraway supernova host galaxies, we can calculate the expansion rate. The leading team doing this, called the SH0ES team, has refined this method for decades. Their latest result for the Hubble Constant is approximately 73.0 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so this means for every megaparsec you go out into space, the universe is expanding 73 kilometers per second faster. Now for the second method, which measures the early universe. This technique uses the oldest light in the cosmos, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. Before this time, the universe was a hot, dense, opaque plasma. Once it cooled enough for atoms to form, light was set free, and that ancient light is what we see today as the CMB. This light isn't perfectly uniform. It has tiny temperature fluctuations, which were the seeds of all future galaxies. These fluctuations created sound waves that rippled through the primordial plasma. Based on our understanding of fundamental physics, we can calculate the exact physical size of these sound waves at that time. This known size acts as a standard ruler. By measuring the apparent size of these ripples in the CMB today, using incredibly sensitive instruments like the Planck satellite, we can determine the distance this ancient light has traveled. Then cosmologists use our standard model of the universe, called lambda CDM. This model says the universe is made of about 5% normal matter, 27% dark matter, and 68% dark energy. By plugging the CMB data into this model, they can predict what the expansion rate of the universe must be today. And the answer they get is about 67.4 kilometers per second per megaparsec. And here is the crisis: 73 versus 67.4. To a layperson, that might not sound like a huge difference, but for cosmologists, it's a chasm. The measurement uncertainties, or error bars, for each value are incredibly small. So small, in fact, that they don't overlap at all. The statistical significance of this discrepancy is now around 5 sigma. That means there's only a 1 in 3.5 million chance that this is a random fluke. In particle physics, 5 sigma is the gold standard for claiming a new discovery. So what's going on? Is someone's measurement wrong? Or is our entire model of the universe incomplete? This is the Hubble tension. The scientific community is now in a race to find the source. One possibility is that there are hidden errors in the measurements. The cosmic distance ladder, with its multiple steps, is a prime suspect. Any small error in one rung can be amplified in the next. Perhaps our standard candles aren't so standard. Maybe the brightness of Cepheids is affected by their chemical environment. Maybe cosmic dust is tricking us, making things look dimmer and farther away than they really are. This is where the James Webb Space Telescope entered the fray. With its giant mirror and infrared vision, JWST can see through dust and get a much clearer view of Cepheid stars than the Hubble telescope ever could. The hope was that JWST would find a hidden error and resolve the tension. The result? In 2024, astronomers using JWST remeasured Cepheids in a number of galaxies. The outcome was a stunning confirmation of the previous Hubble measurements. JWST's data was more precise, but the final number remained stubbornly high, right around 73. This was a huge blow to the idea of a simple measurement error. By strengthening the case for the 73 value, JWST has deepened the mystery and shifted the focus toward a more radical explanation. Our model of the universe is wrong. This is where we get into the exciting possibility of new physics. If the early universe measurement is correct, but the prediction for today is wrong, it means the model we use to connect the two eras is missing something. One of the leading ideas is called early dark energy. This theory proposes that a new type of energy field existed in the very early universe. It would have given the cosmos an extra kick, accelerating its expansion for a short time before fading away. This would change the size of our standard ruler in the CMB, and when you rerun the calculations, it could bring the predicted value of the Hubble constant up, closer to 73. Another possibility is a new particle, the sterile neutrino. We know of 3 types of neutrinos, but some theories suggest a fourth, even more elusive type that only interacts through gravity. If these existed in the early universe, they would have added to its total energy, altering the expansion history and potentially resolving the tension. A more extreme idea is that we need to modify our theory of gravity. Perhaps Einstein's general relativity, while incredibly successful, isn't the final word on cosmic scales. The quest to solve the Hubble tension is far from over. A new generation of instruments is coming online to attack the problem from new angles. The European Space Agency's Euclid satellite is currently mapping the 3D structure of billions of galaxies to get an independent measure of cosmic expansion. A future project called CMBS-4 will map the cosmic microwave background with even higher precision, hunting for subtle signs of new physics. And there's a completely novel method: standard sirens. When 2 neutron stars collide, they create gravitational waves, ripples in space-time itself. The signal from these waves allows us to directly calculate the distance to the collision. No ladder needed. This provides a totally independent check on our cosmic measurements. So the Hubble tension isn't a failure of cosmology. It's a tremendous opportunity. Throughout the history of science, it's these moments of crisis, where observation clashes with theory, that spark the biggest revolutions. Whether the solution lies in a subtle error we have yet to find, or in the discovery of new particles, new energy, or even a new theory of gravity, the journey to find it is pushing us toward a deeper, more accurate understanding of our universe. The cosmic drama is unfolding, and we are all waiting for the next act. Thanks for listening to G Fun Facts Online.